So we've looked at linear estimators now, and we found that if we want an unbiased estimate, we're going to be getting rid of the DC offset, or the plus B term. Now we're going to go in and talk about how to optimize things, but I thought it would be good to have a slight detour and look at an example so that as we are visualizing the math, we'll have something to anchor it to. So in this case, we're going to have some signal, D of n. It's going to be sent through a transmitter, and it will be received on the far end. There will be some noise added. That's our V of n. And then we'll have an equalizer. It's the equalizer that we're actually going to be worried about, but the context is important. So our equalizer is going to be our optimal estimator. And the goal is to estimate what was sent. So a few labels here. The observed sequence is y of n. And our estimate of the sent sequence is d hat. And in between, there's going to be a channel. This channel in this particular example represents the landscape is seen, I guess, by the electromagnetic waves. There will be delay, of course, as it travels from one side to the other. And it turns out we're not going to be too concerned about that delay. We'll worry about, we'll discuss it a little bit later. But also echoes and attenuations of different frequencies. So the signal received will be different from the one sent, especially when you consider that we've added noise to the process. Our equalizer is going to be our filter H of n. In the previous example, we showed that as a possibly as a matrix, and an FIR filtering operation can be expressed as a matrix operation. But right now, just for ease, we're going to express it as just the impulse response of a filter, or the filter coefficients. We're also going to assume that the noise is white and that it's zero mean. We'll later find out what happens if that's not the case, but it's a reasonable assumption for now. So, a random variable, although it's a known sequence in this case, as far as the receiving side can tell, it's a random variable. That's what we're going to estimate, and then just label everything as we've discussed it. Now, how is this adaptive filter even going to begin its operation? We need to have some additional info, something to go off of. If we have no information, then there's not much we can do. We've discussed that. So knowledge of V of n and knowledge of the way this is set up is going to be additional information. And importantly, we will have a training sequence. So this, in essence, is a way for us to observe how the channel operates on some known samples. And the way that works is at the beginning of transmission, some known sequence will be transmitted, and the equalizer in advance will know what that sequence is, so we can begin our operations. We're going to spend more time with this later, but this is just to set this up. It turns out that even as the channel changes, we can use decision feedback equalization and some fun tricks to keep adapting or updating the equalizer without additional training sequences. Okay, to summarize, we want d hat of n to be equal to dn, so we're going to define an error as d of n minus d hat of n. That makes sense. Y of n we can write in terms of what we know. Y of n is equal to our input sequence, our transmitted sequence, convolved with the channel response plus the noise. And then d hat is going to be our filtered version. Now, I've changed notations here again, and we're going to move back and forth between whatever notation is the, I guess, the most convenient in a particular time. But here, H is going to be simply a vector containing each of the filter coefficients, h0 through hm. And y, you may notice I tried to write that in bold, is a vector. And the vector y of n contains the m plus 1 most recent values of our observation, y of n. Okay. Well, what can we do to solve this? Here's one possible solution. We could somehow choose h so that when h is convolved with g, we get a delta function. What this would do is this would give us an output of, well, actually, let me put it down here in just a moment. I want to first note this delta function is delayed, and the delay is to keep the system causal. In general, if we wanted to get the input d of n exactly as it was received, we would have to have something that looks into the future. And that's because g is going to introduce a delay. If you think about it, if we wanted to know exactly what was sent from a transmitter, and we have a receiver that's a couple miles away, we will now receive this, what was transmitted, even if it was perfectly transmitted, with a delay of so many microseconds for the speed of light. And so if we wanted to know what it was when it was sent, we would have to be able to look into the future at our future observations. Obviously, that's not practical. So we assume it's okay if we get what was sent, but with a delay, in this case of n naught. Okay, so now we have, if we had this solution where h of n convolved with g was equal to delta, we would get d hat is equal to h of n convolved with y of n. And we can expand that out. H of n convolved with g of n convolved with d of n. And the h of n convolved with g of n convolved with d of n is just going to give us a delayed version of the transmitted sequence. And then we have our noise filtered with h. So the term that should concern us a bit, I guess, is h of n convolved with v of n. If that wasn't there, everything would be okay. So let's see what impact that has. For starters, we can say, see that since the expected value of Vn is equal to 0, it's white noise, then we have that the expected value of, actually made a mistake there. Oh, no, I didn't. I looked at my indices, and that's correct. So dn should be a delayed version, or d hat of n should be a delayed version of dn. So we subtract d hat minus d of n minus n naught, and that will cancel the expected signal and leave us just with the noise. And the expectation here is going to be equal 0. And you can see that by writing out the expectation, which is, or the argument of the expectation, which is h of n convolved with v of n. And we can write that as a sum. And the expectation will flow through the sum because of the linearity of expectations, giving us an expected value of v on the inside, which is 0. So this whole term is going to be equal to 0, and that's great. So, how do we find h? We could find h by minimizing this particular expression. Here, we said we wanted g of n convolved with h of n to be delta n minus 1. And maybe we can get that exactly, and maybe we can't. But we can get arbitrarily, well, we could get as close as possible, I guess, and get this type of, by minimizing this function. We will see later that this may not be the best case. And we're trying to minimize the squared error, and it may turn out that h convolved with v, while the expected value is 0, the squared error may be huge. And so this, while it looks like a great idea, may not be the best. But it's an example of kind of what we're thinking about. So this would be doable, but really not worth it. We will, to give one brief explanation that we'll spend more time with later. Suppose that g of n had a null, maybe a frequency that it wiped out. Well, the only way then to restore that frequency would be to have a gain of infinity at some point, effectively. And maybe it doesn't wipe it out completely, but almost, and so the gain is extraordinarily high for that filter h of n at a particular frequency. This can be a huge problem because while h of n convolved with g of n may get very close to a delta function, h of n convolved with our noise sequence may be out of control, because the very high gain required to restore what g had destroyed is now going to amplify the noise to unacceptable levels. So one of the reasons why this is not a good idea. But you can see the entire setup is one that can require some more attention, and we'll do that as we look at other ways of estimating h going forward.